All right. So let's start on the let's say the core issue here, yeah, or the core problem, and that is computation versus data, right? Let's start with data. So we are all used to creating in-process data that lives in our memory, right? And then encoding that data, persisting that data, so saving that data, later loading that, decoding it, and getting a memory structure back, right? Data and memory back. So basically, we are used to persisting data, right? And so going through this process, right, like creating an in-memory data, decoding it, saving it, encoding it, saving it, loading it, decoding it, and getting a memory structure back, then we basically say they are supposed to be equivalent. Not even that is a simple problem, all right? That can already be a fairly complex problem. So it's like, that's why a lot of times, right, we'll try to deal with, let's say, simple data structures, right? That can be, for example, JSON serialized, right? That would basically then mean it's a tree structure. It's like, God forbid we have a graph structure, right? It already gets more complicated because we cannot simply serialize, for example, pointers, right? And in memory, expressing a graph in memory is not that hard, thanks to pointers. Like serializing that or encoding it and then later decoding it is already harder. However, it's a manageable problem. We all do it all day, every day, right? However, again, even then, there is like, I think just recently a meme went around on Twitter that used Gollum of Lord of the Rings to indicate this like the bane of their existence, right? Is like serialization and deserialization. Even data is hard, right? But we got it somehow. And the entire core of that, the core idea is that the original datum and then the datum that went through this pipeline, goes through this pipeline, that these two are equivalent, right? That's the whole idea. Yeah? You get the same. Obviously, you cannot get the same, but in the sense of they're equivalent. Data, cool. You do that with data, you're gonna be okay. You try to do that with computation, you're gonna be in trouble, right? It's like serializing, deserializing, encoding, decoding, saving, loading, computation is a very, very hard problem. One of the best environments, mainstream environments, that is somewhat okay with that, I would argue, is actually Python, thanks to their pickling capabilities. And long time ago, somewhere around 2010, I believe, there was a company, PyCloud, which was really ahead of its time, PyCloud, that had movable computation. So you defined a function on your machine, but then you moved that function, executed it in the cloud. Was very cool. They extended Pickle, was what's called Cloud Pickle at that time. And that made it into the standard library of Python. So Python is okay, yeah, but still has its own problems. So you cannot just out of the box, for example, pickle, encode, decode generator. Yeah? So coroutines, right? So it's like, it still has its problems. But in most environments, or for all intents and purposes, all environments, you cannot just store and then load a computation. Therefore, that has multiple consequences, not just one, right? Not just on one dimension. That has consequences, for example, on a reliability dimension. We store data so that we reliably store data, right? So if our process crashes, for example, we can get it back, right? But that's not the only reason. There is a reason of mobility. Like on one process, right? I have a datum. I need to transfer it to a different process. Either in order to communicate, or because this process currently executes my application, later on that process goes away, another process comes up, that now executes my application, so I need to load it from database, right? Yeah. So there is reliability, there is mobility, there is a lot of reasons why we want to store and load data. Now the same can be said about computation. Why wouldn't what is true for data be true for computation? What about reliable computation, right? So it's like I am executing something, the process crashes, right? So wouldn't it be nice if I just got it back the same way as I got back my data? I want to move my computation somewhere. So computation runs a long time, but process goes away, right? And comes back up somewhere else, different machine. Yeah? Then I just wanna continue that, right? That's basically, there are a lot of fancy definitions floating around of what cloud native is, right? My favorite definition is your node, whether that's actually a machine or a container, goes away at any point in time and comes back somewhere else, right? That's my favorite definition of cloud native. Deal with it. Yeah. And so your application has to transparently deal with it. Wouldn't it be nice if we could just store and load computation? Right? Problem is we can't. Right? Most runtime environments don't give us that opportunity. Will they in the future? Maybe. There are some really cool ones out there that are not mainstream, but if you look at Unison Web, Unison Cloud, they have fantastic capabilities, and one of them is that they can serialize, deserialize, persist computation. Really, really cool. But again, the mainstream environments, take Java, take C#, take Python, take JavaScript, or Golang, what we use, Rust, generally, they don't have that capability. But so how are we going to deal with that, right? How are we going to deal with interruptions so that we have reliability? How are we going to deal with interruptions so that we have mobility, right? So we need a different strategy. That strategy is called resume via restart. Right? So it would be fantastic if I had a computation that takes multiple steps. Then I can pause that computation, interrupt it, suspend it. It's all the same. Serialize it, move it somewhere else, deserialize it, and resume. Basically, resume from where I left off. Right? Now, I don't actually need that capability. It's not mandatory, right? What I need or what I want, I don't even want that capability. What I want is an equivalent experience, right? Somewhere where at a suspension point later on, I can resume from whatever we do, it feels equivalent. It has the same equivalent observable behavior of resume. That we can get, right? And that is sometimes called resume via restart, because we restart the computation, or resume via replay. Restart basically appeals to the idea that we're actually restarting the computation from the very beginning. Replay as a term appeals more to the idea that we deduplicate certain events, right. But they mean exactly the same thing. Resume via restart, resume via replay.
And for all intents and purposes, you say computation. We can also say like function execution.
Function execution, exactly. Yeah? A running function execution. And the whole idea of this resume via replay, resume via restart is we recreate what we already had, right?
Right.
And then resume from there. So there is this recreation phase, which we could also call recovery, right? And then the normal resumption.
And you're like, the reason why you want that, right, is because the practicalities of not being able to rely on rely on a process, basically. Like, oh,
That,
a
correct.
process can't live forever, right? You can't say the computation of the function execution takes days or weeks, or um, or that process does go down in the middle of it, and being able to have it be mobile, right? And so that's why you would effectively want that. In an ideal situation, you wouldn't necessarily give a crap because it would just execute to completion. That computation would just happen, but in real life, hiccups happen, and so then you want that ability.
And that is also how it is actually defined, right? So we want the equivalence to an uninterrupted computation.
Yeah.
So, and you also identified the reason, right? So there is always two levels to computation. One level is the, I'm sorry, one level is the execution itself, and one level is the runtime of the execution, right? In an ideal world, which we do not have, but in an ideal world, we have a continuous execution on a continuous runtime. Continuous runtime meaning that there is no interruption, right? There's no crash or anything like that. That is what a continuous runtime means. That's not realistic, right? That we cannot have that. So now what we want is a continuous execution on a non-continuous runtime. We can also have that because the non-continuous runtime limits the lifetime of our execution. So if the runtime goes away, the execution goes away. So now what we want is to compose non-continuous executions on a non-continuous runtime so that they are equivalent to a continuous execution on a continuous runtime. So, and that is what we can achieve via resume via restart or resume via replay, however we want to call it.
Awesome. I feel like I've seen plenty of good diagrams you've put together illustrating the broken up runtime with the continuous execution on top. So
that is true. I got a ton of diagrams on that one. Today I'm gonna go out of my comfort zone and gonna do some live coding. This is like I am willing to embarrass myself because it's like I am a very slow coder, especially when I'm being watched.
So,
but we can actually implement that in a few lines of code.
Okay, awesome. Well, I guess I would like to, for my own education, go back to what you were saying about the difference between resume via restart or resume via replay, and reiterate the difference there. Replay, it indicates more of a deduplication effort where you restart and you deduplicate along the way till you get to the last place you left off. Resume via restart is, can you repeat that part? What is it more like?
Yeah, so there is really no difference between the two. The two refer to the same thing, but they basically emphasize different qualities, right? Or different mechanics. So when you say resume via restart, you emphasize the fact that the same, quote unquote, the same computation has to be restarted. So that is what you're emphasizing, right? You're emphasizing the restart element. So some supervising component, whatever that is, but something has to restart the computation that you just lost, right? So you're emphasizing that part. When you say resume via replay, you're not emphasizing that somebody is restarting it. You're more emphasizing a particular mechanic of how you recover, right? It's like how do you go from the initial state, from your starting point to the point where you left off. And replay alludes to one very specific mechanic. And that specific mechanic is that you memorize, you cache, you store the individual steps that you already have taken until this point.
Got it. Right.
But it means the same thing. The name itself just emphasizes a different aspect of it.
Right. So how would you go about demonstrating this mechanics in
So overall, what we want to do is we want to show that it is equivalent, right, to run something from start to finish, right, to run something to completion, is equivalent to interrupting it and then restarting it and resuming it, right? Or restarting it, recovering, then resume it. So that's what we want to do, and then we want to basically capture that equivalence, right?
Okay.
And I can try this with some live coding. Let's see if that is going to work out well for me or not.
I have faith.
Again, I'm a terrible live coder. This is my very first time live coding. Yeah? So let's see how much I actually gonna make fool out of myself today. All right. So bigger. Maybe that's too big. So we're gonna do a few lines of Python, and there is so much cool stuff already that we can look at. Yeah? So let's start by defining a function. Right? So what we're gonna do? Let's do the following. All right, for yes, but no, we want an array result. Yes, or n result. All right, we got a function. So far, so good.
Okay.
Let's say
I guess I'm curious how we replicate a runtime versus the function execution.
Yeah, we get to all of that. We start baby steps, like real baby steps. What is that thing gonna output?
In this?
It's not a trick question.
Right. 10.
Right? Gonna output a list with 10 elements from 0 to 9. Right? The very first thing that we need to appreciate or acknowledge is, what is X? X does not refer to a computation. X does not refer to a function execution, right? X refers to a value. The function call semantics here are also called substitution semantics, because my function of 10 is going to be substituted with its return value, and that is going to be assigned to X. So we actually do not have a handle to the execution, right? Execution happens, but it is alive in the runtime, in the Python runtime, and I can't get my hands on it. Okay? This is not a running execution. That's why it's called the substitution model. I am receiving, when I call a function, I am receiving the return value of the function. That's the first thing. All right. Now, let's turn this into a generator, also a coroutine. Whoops.
I'm going to convert.
So now what do I get?
Well, it would be.
I'm getting a generator object.
Okay.
I am actually now, X holds a reference to a computation. The computation hasn't even started yet. But it is a computation. So I could do like the return value. Actually, not even bother. So now X is holding an in-flight computation. It's a computation, right? And if I ask X to take a step, then X is going to return, or the generator is going to return the first yield I, which is 0, right? I can do this again, and again, and again, and again, and again, and again. Okay. So I'm actually holding on to a computation. That is already a massive shift in our mental model. X is representing an execution. That is something that I didn't have before. Awesome. That is a fantastic computational primitive to now write our own runtime around it. Because now we can write code that acts as the runtime. Remember when I said the Python runtime holds on to the function execution, right? The Python runtime manages and schedules that function execution. Now we can hold on to a computation. We can hold on to an execution. We can manage it. We can manage this execution. It's up to us now. So that's already super, super cool. Yeah? And so that is going to be the starting point for us. We manage this. We get to manage this execution. But now we have to basically, when we say, hey, one execution is equivalent to another execution, what does it mean, right? So that's, and there are like almost countless possibilities to define what that means.
I have a question for you then. So several of these languages have this yield capability. You create a generator with this yield capability, which is you're showing us holds on to the function computation. What would, I guess it makes me wonder then, why wouldn't at the language level we try and build in a distributed handling capability such that if you're able to store the computation at the language level using Python, that Python wouldn't then have a primitive in place or some in some distributed environment capability to resume that someplace else. It's an interesting thought experiment then. I mean, I'm wondering if you've thought about this, right? Like,
so first, that goes back to what we said in the beginning, right? Where we said it's hard enough to store data, yeah? And store and load data. That's already hard enough, but we do it every day. Figured it out. It's much, much, much harder to store and load computation, right? So if you think storing and loading data makes your life hard, storing and loading computation makes your life infinitely hard. But I also believe that because every application is a distributed application now, it's only a question to what degree, not if it is, but to what degree, that runtimes will evolve in that direction, where we can eventually just store and load, encode, decode, serialize, deserialize computations. Right? There are steps in that direction. that do that for different runtimes, but it's not mainstream. But my prediction is also that if there is a way in hell, it's going to be mainstream. Right? Yeah. It is, however, again, very, very hard to achieve, but it will be mainstream.
Yeah, I can immediately imagine, right? Well, this works because the particular hardware in place, the process running in a particular environment, all the dependencies are there. Like you have all of those things for this particular, where this is particularly running, and then you'd have to ensure all that same exact thing exists on the other hardware wherever you're going to bring it up. So yeah, obviously that
in the same version of the code or a different version of the code, in the same version of the runtime, different version of the runtime, right? Different operating system. So it's gonna be hard. There's no doubt about that.
Right.
It's gonna be hard, right? So it's like before we had something like Unicode, for example, just tried to exchange or ASCII standard just tried to exchange a simple text file between two machines, right? So that's just letters. Yeah. So it's like once you have computation, that's infinitely harder. Yeah. But I believe it's going to be mainstream at one point, because I do believe that, especially in the world of distributed computation, it's just a really, really fantastic quality to have, right? And again, there are environments that either built from scratch, built from or built on top of Vasen, for example. Some modify the interpreters themselves that try to accomplish exactly that, because it is a very desirable quality, very desirable quality, but it's very hard to achieve. So that's why currently, for all the mainstream platforms, we are stuck with, we can't have resume via restore, yeah? Where we just load something. We have to have resume via restart. Stuck with it, yeah? But it works, so it's fine. I say it's fine. Okay, so then, now, what do we want? We want the capability, or we want to be equivalent, whether we resume or we restart, or we resume or replay. Let's call it replay. Or restart? I don't know. So let's but now the question is, what is equivalent? Now it's up to us. We define what equivalent means. So for this, let's define equivalency in terms of effect. What's the effect here? I'm just defining this, all right? I am defining this as whatever the coroutine returns. Whatever the coroutine returns is the effect of the coroutine. So I'm basically taking the trace, yeah? I'm collecting everything the coroutine returns, and I argue that that is its effect, or that is its trace, and I want the trace of the coroutine when it starts and runs to completion be the same as when it starts, gets interrupted, and then runs to completion.
Okay.
So now we could basically say, let's do this. We say execute via resume, right? So just run. Okay. And right, so that's what I want. I want to say, and here we will define execute resume and execute replay, so that they are, not quite. Yeah, I wasn't smart enough for that one. But right, so obviously nothing happens here, right? So So we want this to be equivalent. Let's start with the first one. Resume. Let's just iterate through that thing, right? Let's go through it. Let's run through it all the way, and then see what happens. Actually, we need to do this differently. And then we have oh man. Good thing I have the coding assistant. I'm rusty in Python.
Nice. Can you walk me through this?
All right.
Because I know it's a really simple example, but I'm not super familiar with coroutine semantics here in Python.
So this is just a function pointer.
Okay.
Actually, I can call it func. Yeah, to make sure that this is not an instance of the coroutine. This is not a computation. This is just a function.
Okay.
Right? So, and now for execute resume, super simple. Let's define the effect array, right? And actually pretty nice. Don't know why he does that. So what are we going to do here? We're defining an empty list, right? Effects, where we collect the effects of the coroutine. So we basically just iterate, we instantiate the coroutine with the arguments that we pass here. Python has two different ways of passing arguments, just a normal argument list and then key value arguments, right? So we're basically just replicating that. We didn't really need this here, yeah? But okay. For our coroutine here, we do this. So, and then every single time the coroutine yields, right? We take the value that it yields and then add it to the effects. We don't actually do anything with that value. We can get much more fancy. We can like return a value to the coroutine, right? So like return every value like plus 10. We don't need any of that. We just say, we define here for our simple example, we just define that this is the effect of the coroutine, right? Now I have effects. And when I run that, well, it's not the same anymore, right? Because this one, this one is an entire list. That's my effect, right? Because that is how I define it. 0, 1, 2, 3, 4, and so on. And the other one doesn't return anything yet. So clearly, right, these two are not equivalent. So let's make them equivalent. All right, what have we done? What are we gonna do here? We define two variables. Let's define effects and the history. All right, so what are we trying to do now? Resume basically has a semantic, just taking one step up to the other, right? That's what resume does. With replay, we're trying to do something different. Let's replay to the max. After each and every step, we kill it and then restart it and take one step more, and kill it and restart it and take one step more.
Okay.
So we start with X, right? Now we kill it. We restart it, XX, right? XXX, and so on. Yeah. But clearly, we don't want an effect list of 0, 0, 1, 0, 1, 2, 0, 1, 2, 3, but we want 0, 1, 2, 3, right?
Yeah.
That would be equivalent to this. We don't want that, right? So that's what replay means. We need to catch up to the point where we left off and then take one more step. All right. And that is, again, my brain in a knot all the time. Yeah? But let's try that. Let's see if I get this right. So what we want to do, we want to run all the way to what we have ran to previously, and then take one more step. So do that. Whoa. I'll stop that. So enumerate is a nice little helper that also gives us the index position of where we are at.
Okay.
Right. So now, let's see. If the index is larger or equal to the current history, right? 0, currently on the first one is 0. So then we know, hey, that's something new. That is something we didn't do before. So we want to add that to the history. We could actually also just store the index, right? We want to add that to the history. Oops. So that we remember we have done this before. And then we want to add that, sheesh, kind of. AI wants to bother me a little bit. Yeah, wants to be too helpful.
Sometimes it does that.
And now we actually want to add that to our output, right? The effects. Okay, and since we just did that, right, we want to break out of this. Yeah, we break out of this so that we come around here again, right? And we restart the generator from the very beginning. But then now our history already has an element in it. So now I'm asking the coroutine for its effect. It once again returns 0. But the history already has 0. Therefore, there's nothing for me to do. I'm not externalizing that. I just swallow it. I keep it. I keep it to myself. Now I iterate around. Now it returns 1. Now it's a new element. Because it's a new element, now I actually add it to the history and I add it to the effects. But then because we maximum restart, we stop again, break. Right? Obviously, in a normal system, you wouldn't expect that like after each and every step you take, your coroutine goes away. But that's basically the worst that can happen. So let's just go with it. Okay. And then eventually, when we're caught up to all of that, well, then we want to, when we ran through the whole thing, right, without interruption, we ran to completion. Then we actually want to jump out of that through loop because otherwise we're stuck there. Right? And that's a little bit of a Python quirk. So that else here only gets triggered if no break got triggered. It is a little bit of a melt down your brains moment. So whenever that is triggered, this is not triggered. When no break is triggered, this is triggered, and then we break. So yeah, right, all right. It took me a while. So this is the most succinct way of saying, hey, we ran to completion. All right, we ran to completion without interruption. There's nothing more to do in the coroutine. So I'm done here, right? I don't want to circle around this.
Okay.
But again, it's a little bit of a brain melt. And then we can return the effects, right? And now we expect this to actually be the same. Demo gods. Yeah?
Wow.
Yes, live coding successful. Yeah. So now we expect this to happen again. So, but let's actually look, right, how this unfolds. So the first one, where are we going to do this? Here. So we instantiate the coroutine. And then we produce an effect. And here clearly
It's the same, yeah. Right.
Externalize, emit. Let's stick with externalize. So we produce an effect and we also externalize an effect. Right? Actually, so that kind of lines up. So it lines up on the thing you see better. Okay. And then let's do a similar thing here. So we instantiate the coroutine, right? Every single time here, func, instantiate it. Okay. Then we're asking the coroutine for its effect, right? So we're producing it. There's no argument here. The coroutine did it, right? So, but only here do we externalize it. So this is going to be the first one. First one is going to be pretty straightforward. Right? So we instantiate the coroutine, we produce the effect, we externalize it. We produce the next effect, we externalize it. We produce the next effect, we externalize it. Again, it's pretty straightforward, right? This is how code executes. For the second one, this is wilder, right? So we instantiate the coroutine, we produce the effect 0, we externalize the effect 0. We instantiate the coroutine again, we produce the effect 0. We're not externalizing again. We already did that. We deduplicate that effect, right? Now we produce effect 1, we externalize that. Yeah? Then we instantiate the coroutine 0, 1, 2, right? We only externalize 2 because we already externalized the other one. And that way, we inch ourselves closer, right? So if we go all the way up to here, this is actually not really what happens, right? Or yeah, it is what happens, but we don't externalize this, right? Right, and now we do a little bit like school-like addition. Yeah? What comes out of that? Well, not that far, but what comes out of that is this, right? So that is how replay works. That way, we catch up to the moment, right? We catch up to the moment where we crashed. And then we resume. So there's like this replay via restart. Resume via restart, resume via replay. It has a recovery phase where it goes to the suspension point. And then from there on, it is as if it ran in the first place. And that's the whole idea of replay resume. Now, what I really like about this is that you can show the whole idea in a few lines of code, in a very straightforward code, exactly this else break. I have to look up what that means every single time. But it's like, if you look at that, right? So it's like 10 lines of code, 11. There's like 11 lines of code that implements this deduplication. Of course, in a production system, it's obviously way, way harder, right? It's like nothing ever happens in 11 lines in a production system. But the idea is always the same. gotta have like a computation, right? So there's a computation that you hang on to, and then with that computation, you restart that computation, and then you basically deduplicate the effect that computation already had, right? And now you can ask yourself, whoa, why are we going to do that? What is the difference between that and idempotent? That's a good question. Yeah? And you can also implement the same resume via restart. That's why I actually prefer to say resume via restart, because resume via replay alludes to a very specific mechanic. That is this mechanic where you hang on to what you already did. If all of your operations are of your effects are idempotent to begin with, right? Then there is actually no need for any of that. Then you can just restart, right? Because then the operation, the way it is built, is deduplicates itself. Right? That would be, for example, if the effects, instead of the effects, instead of it being a set, a list, a set, right? So set operations are idempotent. If I add 5 to a set that already includes 5, nothing else is going to happen, right? So then the effect would actually be the same again, right? If we guarantee that our operations are idempotent, then we can basically like skip the entire replay thing. Or in other words, you can now argue that replay, if you memorize the effect, you are making it idempotent. But that is a dangerous argument to make because of the reality of distributed systems and the non-transactionality of things like, for example, executing something and then storing its result. There's always an uncertainty interval in there. So I'm very careful of saying that storing the result of something makes something idempotent. Only in the ideal case, but not in the real case. So, but yeah, that is the underlying mechanic of how a lot of these durable execution frameworks, including Resonate, actually work.
In our case, we're replaying and deduplicating resolve promises.
That is correct.
Yeah.
So in our case, we have two abstractions, right? We have functions and promises. Functions are our computation, right? And or not just our functions are the universal abstraction for computation, and promises are the universal abstraction for coordination, right? So when one function calls another function, when one async function calls another async function, the callee is represented by a promise, right? And the promise is either pending, meaning that the callee has not terminated yet, or it is completed, resolved, or rejected, meaning that the callee terminated successfully or with a failure. And we persist the promise, right? That's why we call it durable promise. We persist the promise, and with that, we can deduplicate. So what I like to say is distributed async await, right? That is Resonate's programming model. Distributed async await is composed, or the abstractions, the underlying abstractions of distributed async await, durable functions and durable promises. Now, the durability of promises, the promise itself, the result value of the promise, is persisted. But the durability of the function itself is not persisted, it is recreated. Right. Based on the durable promises, restarting it and deduplicating on the durable promises.
I think my headphones just died.
Yeah. Yeah, and there's basically no, like, in terms of all of these systems out there, that provide durable execution to, bring back up your computation, mobilize your computation, resume your computation, etc. They're all relying on that same deduplication at the moment, right?
A lot of them do. There are some that don't. For example, the Golem Cloud does not. They actually persist the computation itself.
Oh, really?
Yes, but they have a specific runtime that you need to run on, and that is Wasm.
Okay.
So
okay, that's kind of what that is sort of what I was alluding to earlier, right? So they've actually just developed a runtime
with that capability. Exactly.
Okay, interesting.
But that is a Wasm runtime, right? And just like for all intents and purposes of what we can say today is like Wasm is not the mainstream runtime.
Yeah.
Right? So if you want the mainstream runtimes, then there is no universal solution, right? Or the solution that is attainable universally, right? That is attainable is a replay solution. That is universally attainable because you don't actually need any runtime support, right? So it's like you can build that on top of just about any runtime that's out there. If you rely on storing and loading computations, you need runtime support.
Do you see that as something that's going to get added to the specification over time for for solving these type of problems? Like
there are, so I did a bunch of digging, and you see a lot of people like asking for it in their like language and runtime communities. So you find a lot of issues on GitHub, a lot of questions on forums, right? So whether that's the Wasm community, whether that's, for example, the Kotlin community, whether that is the C# community, there are a lot of questions around, can we make coroutines or generators or tasks or whatever it is called in that particular environment, can we make them serializable? How far are we off to make them serializable? Okay? And that is because it is it's like a very, very cool property to have, because then you can make these durable execution platforms much nicer, actually. So it's a very cool property to have, but it's also a very hard property to like obtain. Right? And again, we have seen this in our past, how much effort it is to like actually serialize and deserialize something, right? And store it somewhere and bring it back to life, right? This is actually a lot of effort. And to this day, there's a meme going around now, right? Where people say, "Oh my God, I hate it." Yeah? It's like you would think, it's a long solved problem. No, still not. Yeah? But for computation, it's just infinitely hard.
Yeah. Yeah, I can see that.
But again, it's a really cool property to have. So I have my hopes up that it's going to be mainstream in the runtimes eventually.
What?
At least some of them.
Well, how would that change? So, I mean, obviously, like, we're taking a bet on it not being
We're not. I'm looking forward to the day.
Really?
Yeah? Very much though.
How would that change Resonate's approach? Like, we're focusing on durable.
It wouldn't. So the thing is, really? Like, we have distributed async await, right? And distributed async await is like built on two abstractions: durable functions and durable promises, right? So we have durable promises. A promise is data, right? It represents a computation, but promise itself is a value, a future value, a value that is not there yet. Yeah? So we can store the promise itself, right? We can store that first class. So we can store the function, the execution, can store the execution. So we have to recreate the execution. If we could store the execution, we would store the execution and it wouldn't change the programming model, right? It would still be the same programming model. You still have durable functions and durable promises. What Resonate is at heart is a distributed event loop, right? That offers coordination across machines and offers supervision across machines. And if one computation here waits on another computation there, and that computation over there eventually finishes and needs to restart or resume this computation, or if we are dealing with a situation where a computation is happily executing, but then the underlying runtime, the process crashes, and that's why we have to restart it, right? That doesn't change. That would not change. It would just make our life on the client side easier, right? If we could just restore that computation. Now we have to restart it. And because we have to restart the computation, we also need the cooperation of the developer. If you want to restart something, it basically has to go down the same path, right? So if instead of me saying that the effect of the coroutine was return 1, return 2, return 3, return 4, the effect is return random value, it's over. Then it's not the same anymore, right? So there's all kinds of questions around determinism and what constitutes equality, and that is like, that kind of goes away when you say, you know what, let me just store it and recreate it. It doesn't really go away. But if the runtime does a really, really good job in bringing back up that execution the way it was when I stored it, right? Then there's like so many issues just like disappear, right? Yeah. But the issue of global coordination, the global event loop, and the issue of global supervision doesn't go anywhere, right? That is still a requirement. That's still required. And that is what Resonate provides at its heart. That replay is nothing but an annoyance, all right? This is like, I do not enjoy the replay. Gotcha. We got to deal with it, but I do not enjoy the replay. That part is an annoyance.
Happily embrace a different implementation when it comes about if the mainstream runtimes embrace it, basically.
Oh my God, it would be so awesome, because then we store the execution, the serialized version of the execution right next to the serialized version of the promise. And then we don't have to deal with two different mechanics. Whereas like here it's store and load, and over here it's restart, resume via restart. Yeah. So then we don't have to deal with that. Yeah. Then we just basically store and load all the way. Awesome.
That'd be cool.
That the replay is not at all baked into Resonate's core programming model, nor is it baked into our core mechanics. It is completely outside of it, because I am hoping for all runtimes supporting that eventually first class, and then we don't have to deal with it. And there are also now, like, there are programming models. What's a computation, right? The question is, what's a computation? Right now we're dealing with functions, right? It's my favorite. But you can rightfully say a state machine is a computation, right? You can rightfully say that. Now, there are awesome libraries, like, for example, XState, right?
Yeah.
That allow you to store a state machine as is, right? They have a serialization of their state machine, and then you can store it and you can load it. So I would love to see, it's like right now it's just a question of resources that we don't have, yeah. But I would love to see somebody implementing a XState SDK, because then we could actually just store what the state of the state machine and then load it somewhere else. Pretty awesome, right? And XState has a whole cool environment with like the graphical editor and whatnot. Yeah. So that is also a completely viable option. It's just like, the question is, how do you want to express yourself? Do you want to express yourself in code, yeah? Or do you want to express yourself in state machines?
That to be or not to be.
To be or not to be. But the point is that the Resonate doesn't care, right? The distributed event loop is the same protocol. The distributed supervision is the same protocol. right? However you recreate that durable execution is completely up to the particular SDK. And I'm the one here just like waiting for, I know it's a pretty convenient situation to be in, to just wait, because very hard to make it happen. But I am the one hoping for the serialization, deserialization of computation.
Fantastic. That was really cool. That was a good breakdown. I think that's probably one of the better. It's a really great basic explanation of replay.
I love the 10 lines of code.
Yeah.
11. I gotta get it down to 10. Yeah. I like the 10 lines of code. It's just awesome.
Try not to make a joke about not being at the conference replay.
Oh, that's right.
Given your ability to decompose that so succinctly, right? But oh well. Cool. Well, that was pretty good. That was good. That was a good. That was a good topic.
One of my favorites, because really you can capture it so succinctly, right?
Yeah.
There's no reason for this mountain of complexity, right? The core mechanic is really very, very small. Right? Again, 10 lines of code small. It's not a production system, 10 lines of code, but it communicates the entire idea.
Yeah. Have you published anything on this before? I feel like this is this would be like a quintessential weekend read.
Oh, have I? Maybe. I tweeted about it once. I actually don't know if I...
Okay.
Maybe I had one. All right. I need to... when I tweeted about it, maybe I also published it on a weekend read. I still need to write this weekend's weekend read. And I am torn between, am I going to write about solving a word puzzle with an SMT solver like S3, or am I going to write about what is the fundamental nature of event-driven applications? Also super interesting.
Yeah, well, that would also be a good topic for us to dive into maybe next Friday.
So much. It's a really cool topic.
Yeah. I like, because you got me thinking quite a bit when you're asking, when I was like, oh, well, event-driven, talking about event-driven architecture, and like, well, is that the goal, or is it just the means by which you're trying to solve your problem, and how many people get wrapped up in that, that cycle there, where, you're not necessarily caring about the fact that things are event-driven, like, let's talk about what your goals are there before you get into an event-driven architecture,
There is a lot we can talk about, and maybe we should talk about event-driven architecture next week. It's like we can do a little poll. Yeah, let's do a poll. Actually, that's cool. Let's ask our community that want to talk about event-driven architecture. But the question is really: do you want to express yourself in an event-driven way, or do you not? Because inherently, every distributed system is an event-driven system. You can't get around it. Why? Because a distributed system is a set of components that communicate by exchanging messages. Right? A message exchange is composed of two events, ideally. Yeah? It's composed of two events. That is a send event at the sender and a receive event at the receiver. Now, unfortunately, distributed systems, being distributed systems, a send event is not necessarily accompanied by a receive event if the message gets lost, or a send event is accompanied by multiple receive events if the message gets duplicated. But in the regular case, right, one send event, one receive event. So distributed systems are inherently event-driven because they communicate via sending and receiving messages via a network. Yeah. So it's not the question of, do we wanna have an event-driven system? That's too late. Yeah. Once you're distributed, it's going to be event-driven. The end. Yeah. The question is, so now, It's like, how are we going to deal with it? Do we want to express ourselves in an event-driven way, or do we want to express ourselves in a, well, now that I say straightforward, in a straightforward sequential way? I prefer that. It's like, but by no means, some people actually do prefer the event-driven way, and there is always a middle ground, where some parts of the system are actually composed in an event-driven way on an application level, whereas other parts are event-driven on only on the platform level. But distributed async await is a sequential programming model on top of an event-driven execution model. So clearly, we are more in the sequential programming model camp. That is, for me, the sequential experience is the ideal experience. It's like it's a quint, essentially, it's a gold standard of developer experience. Step 1, step 2, step 3, step 4, and then I don't really have to think about it.
Fair enough. Cool. All right. Well, we'll save that. We'll save the deep dive into that topic for next week, maybe, and then or run a poll and see what people want to talk about.
Let's do poll.
Yeah.
We haven't done a poll yet.
This is good. Awesome. Thanks, folks, for attending and joining us for the Friday stream of thought. And yeah, this is good. Enjoy your weekends. Thanks, Dominic. Thank you very much for your time. Thanks for doing that. Okay.
Have a great weekend.
Take care. Wrap it up.